welcome to the deep dive. Sometimes the simplest actions, like plunging red-hot steel into cold water, hide some incredibly complex physics.
Oh, absolutely. It looks simple, but it's really material science warfare happening right inside the metal.
Exactly. And today, that's what we're diving into. Quenching. We want to understand that violent cooling, the stresses it creates, and maybe the surprising secret behind modern super strong steels.
Right. How do you make steel incredibly strong using this process without it just shattering? That's the core question.
Okay, let's unpack this. How does that intense cooling actually work?
Ah,
I mean, steel hits water. It cools down fast, right?
well, yes and no. It's fast overall, but the way it transfers heat is really complex and crucially not uniform at all. It actually happens in 3 distinct stages. Kind of chaotic, really.
3 stages. Okay, I always pictured it as just one big whoosh of cooling. So break down that chaos for us.
Okay, so imagine that red-hot steel, say 850 Celsius, hitting the water. Instantly, the water touching it vaporizes. Bang! Creates this little pocket of steam like an envelope around the steel.
A steam shield.
Exactly, that's stage 1. Film boiling. And here's the counterintuitive part. Steam is a terrible conductor of heat compared to liquid water. So this vapor blanket actually slows down the initial cooling quite dramatically.
Huh. Okay, so the fastest cooling method starts slow because of steam.
Precisely. That initial lag is important. The surface is cooling, but the core is still blazing hot. Then eventually that vapor envelope can't sustain itself. It collapses.
And then the water hits the metal properly.
Right. And that's stage 2, nucleate boiling. Liquid water touches the hot surface, boils off like crazy. This is where the heat transfer rate just goes through the roof. Maximum cooling speed happens here.
Okay, that makes more sense. The really dramatic drop.
Yeah, that's the bit people usually imagine. This rapid boiling continues until the steel surface cools down below the water's boiling point.
And then?
Then you're into stage 3. The boiling stops, and the rest of the cooling happens much more gently, just through convection and conduction into the surrounding liquid. Much slower.
So, film boiling, nucleate boiling, then convection. Slow, super fast, slow again.
You got it. And the immediate consequence of this whole messy, uneven process: distortion.
Because different parts are cooling at wildly different rates and time.
Exactly. Even something simple, like a straight bar quenched vertically. The end that goes in first cools faster than the end that goes in last. It's going to warp.
And I bet complex shapes are even worse.
Oh, much worse. Think about a shaft with, say, a keyway cut along its length. That geometric feature disrupts a cooling flow completely. You get significant distortion, holding tight tolerances. Forget it.
So if non-uniform cooling is the enemy of shape, the goal must be uniform cooling, right?
That's the ideal, yes. Which is why, in practice, engineers often try to avoid the most drastic quenches, like straight into cold water.
Right. They might quench more gently, maybe in oil, or use steels designed for air hardening.
Precisely. Or sometimes they add things like polymers to the water. These additives deliberately tweak those boiling stages, slowing things down, making the cooling more even across the part, trying to tame the chaos.
Okay, so we can manage distortion to some extent, but you mentioned shattering earlier. Let's talk about cracking.
Yes, cracking. That's the real killer, especially in high-strength steels. And what's fascinating, really key here, is that the cracking usually comes from 2 different types of internal stress building up at the same time.
2 types, okay.
And we need to remember, we're often dealing with strong steels, the ones that get their strength from a martensitic microstructure. These are inherently less forgiving. They don't easily deform to relieve stress.
Less tolerant of plastic relaxation, you mean?
Exactly. Plastic relaxation is just the material yielding a bit, deforming locally to ease the stress. Think of mild steel, it bends before it breaks. It's ductile. But these hard martensitic steels, they're brittle, they don't have much give, so when stress builds up during that violent quench, instead of relaxing by bending slightly, they just crack. Catastrophically sometimes.
That makes sense. Less give means more prone to breaking under stress. What's the first type of stress?
Thermal stress. This comes directly from that temperature difference we talked about, the gradient between the hot core and the rapidly cooling surface.
Okay.
Let's take an example from the sources. A 100 millimeter diameter steel bar quenched from 850 C into water. Pretty standard scenario.
You get a big temperature difference.
Huge. Early on, the difference between the surface and the center can hit maybe 500 degrees Celsius.
Wow, 500 degrees difference inside the same piece of metal.
Yeah. And a temperature difference that large, if the steel couldn't relax at all, could theoretically generate stress over 1,000 megapascals.
1,000 MPa. That's enormous pressure inside the steel itself.
It really is. It shows you the violence of the process. Now, interestingly, the stress situation actually flips over time.
Flips? How so?
Initially, that cold, shrinking surface wants to go into tension because it's contracting, but it's held back by the hot, still expanded core. So surface in tension, core in compression. That's the start.
Okay.
But then as the whole thing cools down towards room temperature, the core is the last part to cool and shrink. As it tries to contract, the now cold, rigid surface resists that pull.
So the situation reverses.
Completely.
Yeah.
At room temperature, the surface ends up in compression, which is actually good. It resists cracks starting. But the core ends up in tension, and that can be dangerous.
So faster quenching means bigger temperature differences initially.
Which generally leads to higher residual stresses at the end. More compression on the surface, potentially, but also more tension in the core. It's a trade-off.
Okay, that's thermal stress. What's the second threat?
Transformation stresses. This one's down to the fundamental physics of steel's crystal structure changing as it cools.
You mean when the austenite phase changes?
Exactly. When the high-temperature austenite phase transforms into other phases, like perlite, or, critically for strength, martensite, there's a change in volume. The atoms rearrange, and the space they take up changes.
And these volume changes are big enough to cause stress?
Oh, yes. They can be substantial. For instance, austenite transforming to martensite in a steel with, say, 1% carbon that causes a volume increase of about 4%.
4% increase inside a solid piece of steel. That sounds problematic.
It is. Imagine parts of the steel suddenly trying to expand while locked inside the surrounding material. Even transforming to perlite involves about a 2.4% increase. It creates massive internal stress.
And where does this transformation happen first?
Usually at the surface, because that's where the temperature drops low enough first to trigger the martensite transformation, for example.
So you get expansion starting at the surface, generating tensile stress there, right when it might already be into thermal stress.
Potentially, yes. It gets complicated, and the two stress types interact. High hardenability, meaning martensite forms easily, can actually sometimes make things worse from a stress perspective if it forms at the wrong time or place.
So you've got thermal shrinking and expanding, plus phase change expanding.
Yeah.
It's a recipe for disaster.
Oh.
How do engineers fight back?
Well, one key strategy is to try and ensure the most sensitive parts of the steel, often the surface, are in a state of compression when all is said and done. Compression actively resists cracks opening up.
And how do they achieve that?
Surface treatments are common, things like carburizing or nitriding. You diffuse extra carbon or nitrogen into the surface layer. These extra atoms essentially wedge themselves into the crystal lattice, forcing the surface layer to expand slightly, putting it into compression.
Like creating a protective pre-stressed layer.
Kind of, yeah. It's a very effective way to improve fatigue life and resist quench cracks starting from the surface.
Okay, this brings us to something really interesting.
Mm-hmm.
Modern trapeze steels. Transformation Induced Plasticity assisted steels.
Oh, yes, TIP steels. A fascinating area.
These are known for being strong and ductile, right? Good formability.
Mm-hmm.
But they work by having retained austenite transform into martensite during deformation.
That's the mechanism, yes. Stress or strain triggers the transformation of leftover high-carbon austenite into very hard martensite.
But wait, we just established that high-carbon martensite, especially untempered, is notoriously brittle. So how can these steels be ductile if they're actively forming brittle phases inside them? It seems like a paradox.
It really does seem like a contradiction, doesn't it? You're forming tiny bits of ceramic-like hardness inside a metal known for toughness. Why doesn't it just shatter?
So what's the secret?
The key insight here is scale. It's all about the size of the martensite that forms.
Size. How does size stop something brittle from being brittle?
Think of it like a composite material. Imagine you have really strong but brittle fibers embedded in a softer, more ductile matrix, like carbon fibers and epoxy, maybe. If the brittle fibers are very long and you pull on the composite, you can transfer enough stress from the matrix into the fiber to reach its breaking point. Snap.
Right.
But what if the fibers are incredibly short? Tiny little segments. Because they're so short, the matrix material gripping onto the ends can't actually transfer enough cumulative force along that short length to build up the stress needed to break the fiber. The end effects dominate.
Ah, like trying to break a tiny piece of chalk by pulling on it. You can't get enough grip relative to its length.
That's a great way to put it. Load transfer becomes really difficult when the hard phase, the martensite plate in this case, is very, very small relative to the surrounding softer matrix. The stress required for fracture just can't build up within that tiny plate.
So the martensite in trip steels is brittle, but it's formed in such tiny pieces that it doesn't get the chance to crack.
Essentially, yes. The surrounding steel matrix can deform around it, triggering the transformation, but it can't load up those tiny martensite islands enough to break them.
Okay, that makes sense. So how do metallurgists ensure the martensite stays tiny?
It goes back to the initial microstructure before quenching or deformation, specifically the size of the austenite grains.
The grains the martensite forms from.
Exactly. The size of the martensite plates that form is physically constrained by the size of the parent austenite grain they grow within. So if you make the initial austenite grains very small, you force the resulting martensite plates to also be very small.
Control the parent grain size. Control the martensite plate size.
That's the strategy, and the sources detail some really neat experimental work that was done to prove this very hypothesis.
Oh yeah, what do they do?
They took a steel designed to mimic the high carbon content you'd find in that retained austenite in trip steels. Then they heat treated it at different temperatures before quenching.
Why different temperatures?
Because the austenitizing temperature directly controls the austenite grain size. Higher temperature, longer time means bigger grains. So they could create samples with a whole range of grain sizes.
Okay, clever. So they varied the grain size from big to small.
Yep. They went from about 1200 degrees C, which gave quite coarse grains around 410 microns, all the way down to 950 C, which resulted in really fine grains, only about 25 microns across.
Quite a range. And then they crunched them all to form martensite.
Right, creating that brittle, high-carbon martensite, but within different sized parent grains. Then they looked closely under the microscope.
And what did they see? Did the size matter?
It mattered hugely. In the samples with the coarse grains, the ones treated at 1100 or 1200 C, they saw exactly what you'd expect. Large martensite plates and clear micro cracks within those plates.
So the big plates were cracking.
Yes, some of the longest plates looked like they were periodically cracked along their length, just like those brittle fibers we talked about failing under load.
Okay, and the fine grain samples, the ones from 950 C.
That was the clincher. In the sample with the 25 micron austenite grains, the resulting martensite plates were obviously much smaller, and crucially, they were essentially free of any visible cracks.
No cracks at all.
None that they could see in the optical microscope. The fine scale prevented the cracking. They even went further and measured the spacing between cracks in the larger broken plates.
And found a limit.
They found a sort of minimum critical crack spacing, below which the plates just didn't seem to crack anymore. That minimum distance was around 10 micrometers.
10 microns. So keep the martensite plates below roughly 10 microns. And they're too small to easily crack themselves during quenching.
That seems to be the critical threshold
Yeah.
based on this work, yes. Below that size, it's incredibly difficult to get enough stress concentrated into the plate to initiate fracture.
And there was another point too, wasn't there, about coarse grains favoring the longest plates.
Ah, yes, that's a really important second effect. It's not just that coarse grains allow long plates. They seem to have an exaggerated tendency to form the absolute longest possible plates within that grain.
So bigger grains don't just mean bigger average plates,
Mm.
but also a higher chance of getting those really long, problematic ones.
Exactly, which makes controlling that initial austenite grain size even more critical. You really want to keep it fine to suppress those longest, most crack-prone plates.
Okay, so let's try and summarize the main takeaway here for the listener. How does brittle martensite work in tough tree-piece steels?
The reason that untempered, hard, high-carbon martensite doesn't just shatter the steel is fundamentally about size. By carefully controlling the process to keep the initial austenite grains fine, engineers ensure that the martensite plates that form are also very fine, likely below that critical 10-micron length.
And because they're so small.
Because they're so small, the surrounding softer steel matrix simply cannot transfer enough stress onto them to reach their fracture point. They're too short to break easily. It's structural reinforcement at the microscale,
Wow. So we went from this violent, seemingly simple quench
generating potentially thousands of megapascals of stress.
to finding the solution lies in keeping tiny internal features smaller than 10 micrometers. It really is a battle of physics, heat transfer, volume changes, stress solved by engineering at the nanoscale.
Making the enemy too small to fight back effectively.
So what does this all mean for you, the learner? I think it shows that tackling big engineering challenges often means diving deep into the micro-level physics. You can't just design a better shape or find a fancier oil. Sometimes you have to fundamentally re-engineer the material's internal structure, making flaws harmlessly small.
Absolutely. And maybe here's a final thought to chew on. All this evidence we discussed, the critical size effect, it was based on martensite forming due to quench stresses due to rapid cooling.
Right.
But in actual trick steels, the transformation we rely on happens under mechanical strain when the steel is being bent, stretched, or used. The trigger is different.
Ah, so the stress causing the transformation isn't from cooling, but from external force.
Exactly. So the question becomes, do these same critical size rules, discovered under quenched conditions, still hold true when the martensite is forming under active mechanical load? Will that 10-micron limit still apply? Or does the different loading mechanism change the game?
That is a really interesting question. Does the reason it forms change how easily it breaks?
Potentially. That sounds like a deep dive for another time, perhaps.
Definitely something to think about. Fascinating stuff. Thanks for sharing the insights from your sources today.